Okay, so the next speaker is Andreas Klöckner, and he's currently a postdoc at the Current Institute. He is the developer of PyCUDA, a very famous Python library for programming GPUs, and also he has been working on PyOpenCL, which is a more general type of code language for GPU computing, which can be used on ATI cards and CPUs as well. So without further ado, please.
All right, thank you very much. Thank you all for being here, and thanks to the organizers for having everybody, myself included. So I'll be talking about easy, effective, and efficient GPU programming in Python with PyOpenCL and PyCUDA. So when you see PyOpenCL or PyCUDA in this talk or all the following sessions, more or less these two packages are equivalent. And they do very similar things to do GPU programming or programming targeted at compute devices either through CUDA or through OpenCL. I've chosen for this talk to wear more of the OpenCL glasses to make sure that you guys get that perspective as well. To me, CUDA, CL for NVIDIA devices are more or less interchangeable, but CL is more flexible in terms of being able to talk to other devices and other vendors' devices as well. What would I have for you? Today, turns out that this talk is actually the first time, if I have my way, that you'll get to see how to program GPUs. So I'll come through a little bit of architecture motivation into what is OpenCL, how do we talk to CL through PyOpenCL, and then we'll take our first steps into actually programming these devices. And then we'll move on into a better look at what is there in OpenCL in the second session. Third session, we'll get into one of the major reasons why Python in a role as a controlling language for computation, for high-performance computation, is a good idea, and that is code generation. Matt already touched on that. And then in the last session, I'll talk a little bit about I'll show you how to use PyCUDA. I'll show you how to use PyCUDA and PyOpenCL across multiple GPUs. And I'll show you a little bit about my research just in case someone's curious. Okay. So let's get started. So the claim with GPUs somehow is, given this here is an up-close picture. You saw something like that in Felipe's talk this morning. This here is a CPU. And I dug up a picture where you can actually see what parts on this chip do what. Turns out, all this junk here it's not junk. It serves a useful purpose. All this junk here is, like Felipe said, trying to address memory latency. On top of that, there's also a big cache and two little caches that also address memory latency. This here does it in more of a methodical way. This here does it by just cutting the latency. Right, the claim is, in a GPU setting, we can do better than this type of chip design. How would we do that? Well, a more conceptual view of that chip that we saw is this here. Well, to build a processor, you have to fetch instructions, you have to decode them, you have to execute them, and in order to execute them, you need to know what data you're operating on. And then I've stolen these slides from Tabor and Pagelian from Stanford, because I really like them. And so he called this data that you operate on the execution context. Right. So first idea, to me, the GPU comes down to 3 core ideas that make the GPU tick. First idea, get rid of all this stuff on the right. Remove the components that help make a single instruction stream run really fast. So, okay, we've saved some space then. How about a second core? How about some more cores? Well, how about even more cores? Well, great. Now that we've removed all this stuff, we have space for a lot of cores. Now, if we look in detail, the workloads that we have in mind come from scientific computing. So they're, in some sense, doing very similar things to a lot of data. So it turns out, while here we have the facility to control 16 independent, in this example, 16 independent instruction streams, we don't actually need that. these instruction streams, since they're doing very similar things, don't need to be that we don't need all that flexibility. So we can save some more space. How do we do that? Well, instead of having this one ALU controlled by one fetch decode unit, we'll just add a bunch more ALUs. So that's the core idea behind SIMD. You've also seen that in Felipe's talk. And here, for instance, we've added 8 parallel ALUs that do all do the same thing on one decoded instruction. Now that chip that I've depicted here, does that make sense? No. Why not? Exactly, we're computing the same thing over and over again, so we need some extra copies of context. So we need extra room. In addition, there's an opportunity to not just have context that's private to each ALU, but there's also an opportunity to have context that is shared across a number of ALUs. So that's a natural thing to happen along. So integrating that instead of funny. Okay, integrating that turns out we can not just have 16 independent instruction streams with roughly the same space that we had before. We can have 128 independent nodes, 128 instruction streams, 16 of which are sort of independent. So that's great. Last idea that these GPUs bring to the table is, well, all the stuff that helped us deal with the slowness of memory, that we have removed. There was caches, there was prediction, that was out of order execution, so we can go do something else when we're stalled on memory. So what do we do? Well, you've heard the solution this morning again. Turns out we can solve the problem with even more parallelism, and as we've seen, if we add more parallelism, then we also need more context storage. How does more parallelism solve the problem? Well, it's not actual parallelism, it's parallelism that we can fall back on. So suppose we're working on something and this end of things is then waiting on memory. Then if we have some other work that we can turn to and finish there until we run into a stall there, then we're not actually blocked. We keep doing useful work the whole time. And there, simply by adding some more context storage and some more logic in the fetch and decode, we've actually solved the memory problem as well. So these are, in my opinion, the 3 core ideas that make up the GPU architecture in a pretty small nutshell. Right, so this gives us roughly the chip that we're working with, the core that we're working at. Yeah?
They also do other memory parallelism as in
right, yes, sure. Well, I mean, if you build a machine that's this wide, you have to balance it well, having a wide cluster comes as a natural part. Yes, of course. It's not just these 3 ideas, but I think from like 10,000 feet, those are the ideas you would really still see. Right. Okay. So roughly, this is the hardware design. You can't see the individual copies of context anymore, just because we're just saying, okay, let's have say a set number of kilobytes that we're drawing from, and for shared storage just as much. Right. And we said we have a large number of copies of these individual. Right, but this is then about programming a chip like that. And really, how many cores should there be? And if you have a new manufacturing process for that chip next week, how many cores would there be then? How many ALUs are there in each individual core? Well, the answer is who cares, right? You don't want to care, I don't want to care. So the idea then is to program as if there are infinitely many of those. As many as you can accommodate, and same for the number of ALUs. The background to that is if you have a program that expresses the parallelism, transforming that into a sequential program, transforming, yes, the parallel program onto sequential hardware, very easy. Trying to take a sequential program and making it parallel, that's what we've been trying for years and years and years and decades, didn't work. So this here is much easier. And by exposing all the parallelism, by pretending that we have infinitely many cores, and infinitely many ALUs, that's actually a natural thing to do. And this is the right. Now, so now, somehow, we have to take this model here and map it, this idea of the hardware, and map it into a picture where we have infinitely many cores, infinitely many ALUs, right? So how do we do that? Well, we have to preserve the two-scale nature of the thing. We have cores as whole entities, and then each individual ALU. How do we preserve that at the programming model level? We preserve it by having a, well, in this case, two-dimensional grid. Could just as well be one-dimensional or three-dimensional. And saying, okay, we'll group a number of these work items, as they'll get to be called work threads, if you like the terminology better, and say, hardware. So this would be the hardware side, and this would, as I didn't say, this would be the software representation of the two programs, right? Okay, so we build a grid and say the grid is partitioned into these little individual work items. I've got it in the right. So, given a structure like this, how would we map it to the hardware? Well, we map it to the hardware simply by saying, okay, one group goes to one core, next group goes to the next couple of cores, and then we just assign all the groups until we run until we run out of cores to map them to. So as you see here at the end, there are just 3, so we can't assign right now. But that's fine. We're doing exactly what we said was easy. We're transforming the extra parallelism that we have into sequential execution. That's perfectly fine. And then, at the lower level, at the group level, we're doing the exact same thing again. We have, in this case, how many are there? There's 36 work items within each group. And we're trying to map them to just an 8-wide machine over here. So we have to do the same thing. We simply take the first 8 out of each group. Let's count them as 7. Anyway, so the first 8 out of each group, let them execute, and then take the next 8 and take the next 8, and as such we map what used to be massively parallel to the exact width of the machine, and have extra parallelism to drop. And then, so turns out also another thing that I'll mention tangentially now that you maybe keep in mind is that the XYZ order within each group actually does matter, but that the XYZ order among groups does not matter. Why does it matter? Simply because if you look, these guys here, this group gets assigned to these ALUs at the same time. So that gives you a concrete picture of what happens on the chip at the same time, whereas here across these groups, this is also simultaneous, but it's also on a different core, so those are much less closely coupled. So that doesn't tend to matter. To pick the other thought back up, what this programming model provides for you is just a pool of parallelism for the chip to draw from. And then you execute this in as parallel a fashion as you can. And if you run out of parallelism on the chip, you just transform to sequential execution as necessary. Right. So that gives you, in a nutshell, both the CUDA and the OpenCL programming model. So in that sense, OpenCL was modeled on the CUDA model. So at the very end, obviously, the next bunch of work in that. Right. Now, how would this look in the setting of an actual program? Well, turns out from your perspective, from the perspective of a program, it looks like one single function runs this many times, runs for every square in this whole grid. How do you distinguish then where you are in this grid? Well, you have to be able to get indices into this grid. And in OpenCL, it turns out you can get that by asking for local ID, group ID, and for a global ID. That's pretty much exactly what it sounds like. You can ask for your position relative to the origin of your group. So for example, this guy here, its local ID along axis 0 would 0, 1, 2, 3. Along axis 1 would be 0, 1. And just as, and like that, its group ID would be 1, 2, 3, 4. No, 0, 1, 2, 3. And along the other axis, just 1. And its global ID would, well, you'd have to start counting all the way over here. That gives you a comprehensive way of accessing indexing information. And then you simply write a function that uses this indexing information and accesses data based on where you are in the grid. This grid doesn't necessarily have anything to do with how your data is laid out in memory. It's just a number of function invocations that you're free to do with whatever you want. Right. And as I said, 2D is not a God-given here. It could as well be 3D, 1D, whatever you want. Okay. So that summarizes the programming model that we're supposed to work with. Now, that's not the core message of this talk, of course. I just needed you to know all of that. You'll learn more of the details in Felipe's lecture sequence. But since we'll be doing a little bit of GPU programming later on, I just needed you to know that. Right. So, I've been saying OpenCL a lot. What exactly is OpenCL? OpenCL is the open computing language, an open royalty-free standard for general purpose parallel programming across CPUs, GPUs, and other processors. Right. Sounds complicated, really isn't. You guys have heard the word CUDA a lot as well. As far as they target NVIDIA GPUs, OpenCL and CUDA pretty much do the same thing. Now, if you want to just target NVIDIA GPUs, you might ask, why should I care? Why should I care whether I'm talking in CUDA or OpenCL? Well, the main reason for me to emphasize that OpenCL is a good idea is that it lets you do runtime code generation out of the box. And we'll talk about the benefits and uses for runtime code generation later on in lecture 3, but as I said, Matt already mentioned some of these. In my opinion, it's a good idea to have this around, but also there are other benefits. Obviously, you can use OpenCL not just to target GPUs. You can also program your CPU with it, and use it in a role that's similar to OpenMP, although it's slightly more complicated to do similar things. So in that sense, it's also a rather flexible way of talking to any kind of compute power that might be available in the box under your desk. And it defines a host-side programming interface that comes as a library that you link into your program, and it defines a device-side programming language. Those combined make up OpenCL. How did it happen? Well, a bunch of companies, including NVIDIA, got together and wrote a specification that initially came from Apple. And over time, it got proposed in June of 2008. First specification got released in December of 2008. Then in May of 2008, there were actual implementations of it. In the second half of 2009, there were multiple implementations, and in June of 2010, there was a revision to the standard that ironed out a few bugs. The idea behind it is, yeah, question? No, sure. Are you stating that nobody uses it? Or? Well, right. In my opinion, yes. So first of all, it starts with people. Well, without the standard being implemented, nobody cares. And fact of the matter is there are at least 3 high-quality implementations. There's one by, well, 4 if you count different targets. There's NVIDIA's GPU implementation. There's ATI's GPU implementation. There's AMD's CPU implementation. There's also an implementation out of IBM where they map OpenCL onto power hardware, I think. And lastly, yes, Apple, obviously, right, who originated that. So everybody who owns an Apple laptop that right, no, it's been around 2 years less than CUDA has, right, and so that settles the first part in my opinion. Well, okay, OpenCL has 2 years of aging and of maturing behind it, and to me, I've not encountered major issues in using them. That's the only thing I can say. Turns out also that I've taught a class at NYU. Eduardo and Ken have attended that class, and my personal experience was teaching it was not a major issue, and actually several people from the class then took to CUDA hardware that they wanted. That was an issue. So in terms of teaching, I thought that was a good idea. But so, do people use it? People, first of all, I think I've answered. Do people implement it? The answer is yes. Do people use it? In my opinion, also yes. It tends to be less visible, simply because there's one big outlet for these kinds of things, and you all know where that is. That's on the NVIDIA webpage. Nonetheless, I've seen a number of things being done with OpenCL. You need to put it into perspective for CUDA having been around longer, obviously, but also we've implemented some of the same stuff with CUDA and OpenCL, and I'll demonstrate. It's really not that big of a conceptual jump, and speeds are pretty much exactly the same as you would expect from something that exposes the same concept. Does that answer your question? Yeah. No. So that was a long-winded answer. So why am I doing this? Perhaps it's not so bad. Yeah. No, I've used it. I'm happy with it. And, if you view this as promotion of OpenCL, that's to some extent true. I think you should at least check it out and take it into consideration. I don't think it hurts if you know that yet. Right. So the core idea is there's not just GPUs, there's not just CPUs, there's compute devices, right? Things that can compute and that ideally compute in parallel because they have multiple cores. And this is pretty much where OpenCL is located, what you want to be able to talk to, this compute power using OpenCL. And to tell you, to show you, if you have an existing CUDA program, or if you have an existing OpenCL program, how much effort is it to take it to comply to the other standard? If you squint a little bit, you'll be able to see that these two programs, on this side is some OpenCL source, on this side is some CUDA source, actually look pretty much exactly the same. It's you need to change, say, thread IDX.y to get local ID of 1. Big deal. It's really conceptually not very far, right? So in that sense, you'd also expect that, if there are performance differences between these two programs, they're entirely artificial. Right. Okay. So that gives you an idea what OpenCL is. You don't know much CUDA yet, so this isn't that useful to you, but it just supports the point that there's a one-to-one mapping of concepts between the two. what does the world look like from the perspective of OpenCL? Well, first of all, it starts with a host. This is the traffic hop. This is where the runtime interface that I talked about earlier lives. And then there are a number of compute devices. Here in this instance, there are 4, and they're grouped into platforms. Each of those, you see this here, platform 0, platform 0, platform 1, platform 1. Each of those has its own separate memory. That's something. That's an assumption that is baked into the standard. And each of these platforms, for example, would be supplied by a different vendor. So, example, platform 0 might be CPUs talked to through an AMD implementation, and platform 1, could be GPUs that you talk to through an NVIDIA implementation. And all of those peacefully coexist, and you can pick exactly what you talk to. And what does all this terminology mean? Well, a compute device is something that has a memory interface, something that has memory attached to it that you can transfer data into. And a compute unit within that is what corresponds to a core, as we described in the architectural overview. And lastly, a processing element is otherwise somehow commonly called SIMD lane, or as we said earlier, an ALE. That's some of the terminology, and then the idea is that we'll use Python to talk to this end of the universe. We'll have Python running on the host, and we'll keep talking to these devices here in the device programming language, which is somehow a sub and a superset at the same time of C99. Or it has a non-empty intersection. I was corrected once with C99. Right. So that's the picture, and that's where PyOpenCL comes in. That it allows you to do all this fancy computing on CPUs, GPUs, what have you, from Python. And in that sense, it's somehow a godsend, because people have bashed Python because if you loop over a long array of stuff in Python, then you die of a horrible death because it's so slow. So what do you want? You want to be able to do whatever you want to do in that loop in compiled code. Well, guess what? CL is a compiler in a box. You give it a string, you get executable code back to execute it, and you don't. If you wanted to do something like that previously, you brew some hacks with calling the compiler from your script, loading the result back into your existing executable, and then calling that. OpenCL makes it. It's a compiler in a box, and that's a very useful thing to have, and that's why I am excited, because it seems to be the right thing. Right. Yeah.
Are there other kernel themselves, or the syntax itself?
Right. Why does it make sense? For a number of reasons, and more or less this whole sequence of lectures is aimed at convincing you that it doesn't. Productivity gains. Productivity is hard to measure. I argue that they're there, but that's a very individual thing. It depends on how proficient Python programmers are and all of that. So some tangible. I'll get to some tangible benefits that you say these are lines of code that I don't like.
Is your kernel in Python? The actual
the kernel is not in Python. Yes, but I mentioned the word code generation, right? So imagine having to do code generation in C. Being able to do string processing easily is one of the big selling points of Python, right? So that is one thing that you can easily do from Python, where these two are a good fit. Right? Have a way of talking to a high-performance compute device from a high-level language where you don't have to worry about very many of the details. And this plays very nicely into this slide here exactly. So is your question sufficiently answered for now? Given that we'll see an answer as we go on, too. If not, ask again. Yeah, another question. Well, it's a C compiler in the form of a library. That's correct. So in CUDA, you have in CUDA, if you have C-level code, what you need to do is call NVCC with your CUDA source code, and you get a binary back. That's the conventional way that that you operate when you write a computational code. You write code, you compile it, you run it. Now the idea behind using Python somehow is it's a scripting language. Right. Sure. In the case of in CUDA you can't only hand the CUDA interface a PTX kernel to compile at runtime, not a C-level kernel. If you want to do that, you have to pipe through NVCC yourself, and that's something that PyCUDA can do for you. OpenCL ships with this capability natively, so that you can just hand the OpenCL runtime a string that is C source code, and it gets executed right then and there. So, in that sense, you have. You might say that it's an interpreter because you specify code at runtime, but it isn't. It is a full-fledged compiler. Code gets compiled right then and there when you hand it, that function of the OpenCL interface your string, and it is a full-fledged compiler. There's no interpretation. That's why I mentioned Python particularly. This distinction between compile time and runtime is entirely artificial. There's no reason why that should be there. It's just because compilers were these big lumbering beasts that nobody wanted to link into their program. But why? So in that sense, runtime code generation is a distinguishing feature. Question answered. Okay. It's a just-in-time compiler in the box, exactly. All right. So why does scripting for GPUs make sense? Again, this doesn't hit the productivity angle as much as probably was contained in the previous question. But why is it a sensible thing to do? Well, for certain, it's scripting languages and GPUs are complementary, right? GPUs are very parallel, they're very fast, they care to some extent really about how they are programmed. For Python, pretty much the opposite is the case. It's really not that parallel, it's really not that fast, and it really doesn't care exactly where it runs from a cell phone to a big supercomputer. It's pretty much the same language everywhere. And if you look at these two spaces to be in, it seems to be that Python does well for a certain kind of code, and that GPU code does well for another kind of code. So, in my experience, it turns out that computational codes contain some of both of these kinds of code, and it makes sense to have the capability to be able to do low-level fast things and high-level high-level things where you don't care about possible slowness. In addition, if you're programming GPUs, the CPU is restricted to being more or less just a traffic light, right? So you have to do something maybe 1,000 times a second where you poke the GPU, do this, transfer that. And scripting is plenty fast to do all of that. And that's the premise for both of these packages. Take Python and CUDA, you get PyCUDA. And Python and OpenCL gives you PyOpenCL. And I don't mean to be religious and say, you should be using PyOpenCL just because there seems to be a heavy emphasis on CUDA. That's why I chose it. But let's tell them something about it. Both of these packages will continue to be maintained. Just scatter and doubt may have. Right. So, without any further ado, what does it look like? What can PyOpenCL do for you? Right. Okay. Here's some source code. I hope you guys aren't scared by source code. Here's an actual full GPU program. We import PyOpenCL as an alias name CL to make it shorter, and we import NumPy. How many of you are familiar with Python, by the way? A good bunch of you. Okay. If you guys are confused by Python syntax, then either just ask, or Python is built itself as sort of readable, so maybe you'll be able to get it. Right. Okay. So we import PyOpenCL and NumPy, which is an array package. Matt mentioned that as data transport. That's also curiously the role that, well, not curious, not very surprising. NumPy here satisfies the role of data transport in addition to allowing array computation. So what do we use it here for? What do we use it for here? Well, we start with some size array of random numbers that we catch to single precision floating point. Then we create ourselves a OpenCL context. That's just a living space for all the OpenCL objects that we might need. We create ourselves a command queue in that context. And in this here, we've made choices about which device we live on, which platform we live on, all of that. And I'll have more detail there in the next lecture on Wednesday. Right. So given this context, we can then create a buffer, which is a space of memory on the device, into which we transfer. No, we don't actually transfer. Here, so we just allocate a chunk of memory of the size of A that we declare to be read-write memory, and then we transfer, given this command queue here, data from this NumPy array A onto the GPU, into this A device space that we allocated from line above. Then, now that we have the data on the GPU, remember from the picture that every OpenCL compute device has its own memory. So this is a necessary step. All the data needs to go over. So now that we have the data over, let's try and do something useful. So in this case, we're trying to do something really simple. We'll just multiply each entry of the array by 2. How do we do that? Well, we create a CL program, and then between these triple quotes, this is a whole string in Python. Because they're triple quotes, we can include new lines within the string, so we can just have our source code right here without any interfering characters. Right, what does the source code look like? This bit here in particular is compute kernel. Say kernel, then something that looks like a C function with a little bit of junk that may look a little bit foreign. So the function itself is declared kernel, and then this pointer A is declared global, and then A at index get global ID along axis 0 is multiplied by 2, and that's already the entire code. Is fed to the constructor of a program object that we then build, and this is the part where the just-in-time compiler comes in. And once we have the program compiled, we can call it in that command queue that we allocated up here with a grid that is exactly the size of A, and that has a work group size of 1 on this buffer A depth. And at this point, the GPU will actually go out and multiply a good bunch of floating point numbers by 2. So this is possibly the simplest possible program that you can write using PyOpenCL. Then you can go ahead and actually get the data back out. So I've just scrolled all that stuff a little bit back up, and I make a new NumPy array, and I read the data back off the GPU and check that the actual write result came out. Not particularly surprised. Let's make some more changes to this program just to get the programming model into your head a little bit more. For example, let's worry about this size over here, this work group size, the local work group size. For example, say I change this here to 256. What would happen? Any idea? Who thinks the program would still run flawlessly? You're either not here or you're wrong. So unlike CUDA, which is what you may be thinking, in OpenCL we specify the global size already multiplied by the local size, by the group size. So if you're coming from a CUDA mindset, that's the one big difference between OpenCL and CUDA, that for grid size you have to multiply by the work group size already. Not such a big deal. The benefit of being able to do so, the global grid size stays the same no matter how big we make our work groups. So I can change the work group size and see the resulting performance difference. Meaning, in this case, I just mapped one single floating point number to each core. And if I change it to 256, all of a sudden I map 256 floating point numbers to each core. That's a very tangible performance difference. But this global grid size has not changed as a result. Right. Okay. So I can change this. Yeah. Matt.
I guess I don't get what's going on for OpenCL. Like, if I make it more than can be mapped to like a given SM on my little 9400M that I have in my laptop, and then I have things in there like everyone needs to see this shared piece of shared memory.
It's the same thing as specifying a little block that's too big for your SM in CUDA. You'll get an error.
Oh, okay.
Yeah,
Okay, so
it's one-to-one.
Magically, yeah.
No, it doesn't do any magic. There are size upshot of Matt's question here. There are size limits to how many things you can pack into each work. Like there are size limits to each block in CUDA, if you're familiar. Right. Okay. Also, one thing that you tend to have to do a fair bit in CUDA and OpenCL is index map. So let's just expand out this get global ID. You can equivalently write that get local ID plus get local size times get group ID. Results in precisely the same thing. The program stays valid here. It's also changed the group size to 256. That's all exactly perfectly valid. All right. So here are a few things for you to puzzle over. How would you change this program in Python? Instead of just multiplying one array by 2 to compute an element-wise product of 2 bits. Give you a few seconds to think. Well, it's not that hard. You just need 2 more buffers and then a few more pointer arguments to your kernel. You need to pass those in, and that's pretty much all the changes that are required. Here's another one. How would you change it to use groups of 16 by 16 work items? So instead of using a 1D grid, that's kind of more natural for our 1D array. What if we artificially wanted to use 16 by 16 work items? What all would we have to change now? Give you a glimpse back at the source code. Well, is there a blackboard that I can scribble on? Not really, right? Ah, okay, so it's that. So it turns out then that in this case, the global size needs to change because global size and work group size always have the same dimensionality. So you have 16 by 16, right? And then however many work groups that comes out to, you have to just, well, you can then say this axis will stay 6 work group size, but that along this axis you'll have to use as many multiples of 16 to match how many work groups you have. Right, okay. That settles that. How about this here? How would you benchmark one work item? How would you benchmark using one work item per group against using 256 work items per group? What would you have to do? Think for a tiny bit. Well, the key thing to realize is that the GPU and the CPU are also, if in OpenCL you're talking to the CPU itself, the CPU is telling itself what to do in a kind of schizophrenic way, then that part, the actual computation, runs asynchronously, from the control program screen. So in order to be able to do meaningful timings, we have to issue this this kernel lock and then wait for it to complete. So and you can do that by just appending at the end here a dot wait. And so you measure, you write down the time here, you put the dot wait here, and you put another time measurement at the end. That gives you a crude way of benchmarking what's going on. There is an event. So it turns out, I was not trying to go into all that much detail, but it turns out what you get out of this here is an event that has a method dot wait. So thereby you automatically can do that. Right. Okay. So yes, events are mostly glossing over. Right. So that gives us a way to benchmark. Yes.
So is there
Sure. That. No, I didn't. Yes. Oh yes, down here I need to. Up here I do not. Why not? I'll talk. That's right. Matt has the right idea. All of these guys get one argument called the queue. The queue means, one happens after the other. So by the time we finish this wait here, we're guaranteed that everything that went onto the same queue also is guaranteed to finish. Right? So yes, if I want to read stuff back out, then I need to wait for that read to finish. Right. Okay. So that's that. A few more general points about PyOpenCL before I close for today. How am I doing for time? 15 more minutes. I'll be done. I'll be done a fair bit before then. So give me like 5 more, and we'll be able to move on. Right. So what's the idea? Well, the idea behind both PyCUDA and PyOpenCL, that they wrap up this CUDA and OpenCL functionality, right? So they provide complete access to the underlying layer. So so far, we have a pretty good track record of when there's a new release of stuff, then we have support for all the new things that are exposed within a couple of days. And well, if you're trusting your code to a wrapper, you definitely want to be able to use all the facilities that are exposed at the lower level. Another thing that I haven't emphasized previously, but also plays into the question that we had, was how does it increase your productivity? Well, it increases your productivity by managing resources automatically. So in your code, some people neglect to write error checking, some people neglect to write proper resource management code to free all the resources that they've used. In PyOpenCL, you don't have to, because the system does it for you. The garbage collector takes care of properly, knowing when things can be freed. In addition, one gimmicky thing that you can do in PyOpenCL, you can use the GPU interactively if you care to. You can write all these things out in the pipeline shell. It's actually kind of fun if you're just trying to see how a few things work. Also, it integrates tightly with NumPy. We'll see a closer example of that at the very end. And in terms of being complete, so for example, a lot of things that OpenCL lets you do is finding out what's going on, finding out information. At the C level, these come in the form get info, something like get device info, get something info, and all of these are in PyOpenCL. The images, samplers, memory maps, kind of more and more obscure features. Well, profiling isn't, synchronization either, but all this obscure stuff is in PyOpenCL. It also works on all 3 major operating systems and some of the stranger ones. Yes? Yeah, I can hear you just fine. So there's an NVIDIA vendor extension that PyOpenCL also wraps for you if it's available, where you can just get the compute capability of a device as such a get input query here. So you can find out compute capability.
Does that mean
Atomic operations come as part of there's part of the standard, and so obviously you can use them if they're available. If they're not available in the hardware, I don't think the NVIDIA implementation makes any attempt to emulate them. Is that okay? Right.
Is it more complete? For instance, CUDA will give you the megahertz for the memory bus, but not for the processors. Is it possible to compute, the plot to byte ratio based purely on the code that I get out of it?
I don't know off the top of my head. It's fairly complete, as in for a device there's a long list of stuff that you can find out. I can easily check later. Right. Okay. Did everybody hear that question? Another question?
instead of embedding the protocol of OpenCL as a string, is there a way to express the computation through Python and having that translated to runtime to a...
Absolutely. That's kind of what you would do in a code generation setting, right? It's just a string. You can come up with that string in any way you please, but very much to me that's something that would be built on top of PyOpenCL, because the string representation is really the simplest it gets. That's what OpenCL itself thinks in terms of, because there's a C compiler that turns that into executable code, right? That said, if you just wait another 2 or 3 minutes, I'll show you the first example of where code gets generated. Is that question answered? Yeah? Okay. Any more questions? I like this. I like it if it's interactive, if you tell me what I need to be telling you. All right. So yes, stuff is in OpenCL. PyOpenCL runs on stuff. And as I've already said, most of this stuff here. One key point is if you're dealing with scarce resources like memory, and if memory is being managed for you, then there can be a situation where the garbage collector thinks, well, this particular piece of memory we better hold on to because someone is spuriously holding a reference to it, when really it's not of any particular use anymore. So in those situations where you're really pushing up to the limit of the device memory and you want to be able to use all of it, you can do your own resource management if you absolutely have to. That said, we try to, PyOpenCL also tries to be smart. It runs up against the memory limit and it tries to run the garbage collector and then tries again to make sure that, if there are no spurious elements. And also, PyOpenCL deals correctly with having multiple contexts and makes it relatively easy to talk to multiple GPUs from one thread, something that you can't really do in right. And in general, the rule is like in any garbage collecting language, as long as stuff is reachable through some path through references, then stuff won't get freed, and otherwise it'll get freed at some undetermined future time. So that you don't have guarantees as soon as you lose a reference that stuff will get freed, unless you do this. Right. There's documentation. This doesn't look like documentation. Trust me, it is. If you Google for PyOpenCL, you find it. It's complete reference documentation, also a little bit of motivation and explanation. And it's available at this address. There's complete documentation. It's under an MIT license, and all you need is NumPy and Python 2.4, and there's a nice mailing list where people hang out. As a last thing, also the first instance of code generation is actually in action. Here's an appetizer. Make sure that you come back to the next lectures. So you remember your first PyOpenCL program where you multiplied arrays by 2. Well, it turns out here we just have our NumPy, our 4x4 or whatever array of single precision floating point numbers. And we import a new module that you haven't seen yet here called CL array. Okay, CL array 2 device. And we get some object back that represents this array. And we can multiply this array by 2 and get it back. And so that comes back to answering the question that we had back there. Does it make you more productive? Possibly. Does it save you work? I would argue yes. And those two sometimes correlate because you don't have to code up trivial stuff that you would otherwise have to reinvent an extra kernel for if you just need to add to arrays of numbers. PyOpenCL can do that for you. Have a reduction or have a scan, things like that. Okay. That's pretty much all I wanted to say for today. If you have further questions, I'd be happy to take them. Anyone? Yeah? Compiling Python for GPUs? I guess it's different. It's a different thing, right? So there's one project called Lider. But their big selling point is that you write something that looks like Python all the way, and then that gets transcribed into OpenCL C and then run on the device. That's an alternative approach. Personally, I don't like it very much because it takes this advantage of being able to do code generation right back away. Because then again, I'm all in one language, I'm all in one Python script, and then without doing funny things, I can't easily generate the Python that I'm executing within that same server. I can write function definition and eval that and stuff like that. And that's where it gets to be grungy. Where here is, there's a clear set of rules. Give me a string, I'll give the executable. Give me a string of C code, and I'll give you the executable. What if the programmer doesn't know C? Should he or she be allowed near a GPU? I don't know. It's not a problem that I'm trying to solve. All right. Any more questions? Yeah. Easy. You just make you can. Turns out you can make one context that talks to multiple devices in OpenCL, or you can make multiple contexts, and you can do all of that from one thread or from multiple threads or MPI parallel or whatever you want. No, I mean, I'm tempted to pull up to Wednesday's lectures, but in principle, really, it's simple. So in OpenCL, everything is kind of explicit. Every call gets either a command queue or a device that you wanted to run on, and so you can orchestrate your whole big computation from one stream of instructions. Yes, I'll answer that later. Okay. It's actually simple.
Later will be true. Later is fine.
Yeah.